Part 1. General Update. There is a comet out there that shouldn't exist. It is called Atlas, and now, new information from an experimental satellite, published on October 14th, 2025, has reinforced this, using over 9,000 images. The new findings reveal what appears to be a deliberate cover-up, and tonight, we will unveil this new evidence to solve this mystery once and for all. And beyond the news about Atlas, we will explore a mysterious star that pulses every 44 minutes with radio waves and X-rays, and no one knows why. Could it be a new member? In the catalog of mysterious cosmic objects, we will also shed light on 4 coronal mass ejections that are heading toward Earth, and their effects may be felt and seen this week. And finally, we will look at the ghost particle, a neutrino so powerful it breaks all records, striking Earth with an energy once thought to be impossible. Stay with me until the end, because what we are about to discover together will fundamentally change how you think about what is watching us from the shadows. If these mysteries intrigue you as much as they have intrigued me, be sure to press like and subscribe, so you don't miss any updates as these stories unfold in real time. Leave a comment letting us know where you're watching from, and what time it is there, and whether you believe we are being told the whole truth about these world-changing discoveries. And if you want to help this community grow, please share this video on X, Facebook, Reddit, or even just in your group chats. You are the reason we can continue to pursue stories like these. So, thank you for your support. Part 1. Atlas and the Tale of the Missing Tail, upending the simple comet narrative. Imagine a night sky filled with telescopes, each one worth millions of dollars, all pointed at the same target. Hundreds of instruments, from ground-based observatories to spacecraft, drifting in the silence of space, all tracking a single object. As it hurtles through our solar system, now, imagine that the most sensitive of these instruments, after stacking more than 9,000 individual images, revealed something no one expected on October 14th. 2025, there was no tail. Astronomers announced the results of a massive data analysis from TESS, the Transiting Exoplanet Survey satellite. They had captured more than 9,000 frames of Atlas, an object from interstellar space that had been puzzling since its discovery. They stacked those frames together, a technique known as co-adding, which is designed to separate a faint signal from noise. When you stack images like this, you are essentially adding up all the light, frame by frame, until even the faintest structures become visible. It's like listening to a song that is almost inaudible, and turning up the volume with each repetition until you can finally make out the lyrics. What Tess found, or rather, what it didn't find, was extraordinary. The object appeared as a point source, a single dot with no extended coma, no diffuse cloud of dust and gas spreading outwards, no tail streaming away from the sun. When they measured its radial brightness profile, which is how the light falls off as you move away from the center, it dropped off just like a star, not like a comet. Stars are point sources because they are so far away that even their immense size collapses into a single point of light. Comets are supposed to be different. They're supposed to be extended, to show structure, to have that iconic tail that has inspired awe and terror for millennia. The point spread function, or PSF, is the pattern of light you get from a point source. After it passes through a telescope's optics, every telescope has a PSF, and it's like a fingerprint. When Tess looked at Atlas, it saw only that fingerprint, and nothing else. The analysis team was able to quantify exactly what this meant. If there was any dust above a certain surface brightness, they would have seen it. The stacking process increases the signal-to-noise ratio dramatically. So much so that even very faint features become detectable. They could derive limits on the dust density, particle size, and ejection velocity. All the numbers pointed to the same conclusion: any dust that might have been there. It isn't behaving the way cometary dust should. However, other observations tell a different story. And this is where things get strange. JWST, the James Webb Space Telescope, has detected water vapor and carbon dioxide around this object. Spectrometer measurements show a mass loss of volatiles escaping into space. These are the telltale signs of a comet, doing what comets do. But where is the tail? The visual evidence of all that material escaping. You're pushed into a dilemma here. Either the coma is too compact, too dense, and unusually confined, to the point that it remains invisible to optical telescopes, while still producing detectable gas signatures. Or something else entirely is happening. It's like seeing a fire burn, and seeing no smoke rise. Or the smoke is being compressed to the point of invisibility by some mechanism we don't understand. Or what we're calling a fire isn't really a fire. The contradiction is there, inescapable. Tess has spent months staring at this object with one of the most sensitive instruments we have ever built for detecting faint, extended structures. It sees nothing. But other instruments, tuned to different wavelengths, different physical processes, are signaling that something is definitely happening. One of these observations is missing something crucial, or our entire framework for understanding what a comet should look like is about to be broken. And this is the thing that gets me. We've seen comets do strange things before, but we've never seen them do this. We've never had an object perfectly mimic a point source, while simultaneously showing the chemical signatures of strong activity. The numbers don't just not add up. They actively contradict each other. This isn't a minor discrepancy that can be explained by the conditions of different observations or equipment glitches. This is a fundamental disagreement about what the object is doing. Tess's data is now public. Anyone can download it, run the analysis for themselves, and check the numbers. The result is reproducible. The non-detection of a tail is solid, which means we need to find out what's going on, because if we cannot explain this with conventional comet physics, we will have to start considering explanations that sound unsettlingly strange. But before we go there, we need to understand just how deep these contradictions run, and why different instruments are painting such completely different pictures of the same object. Part 2. Contradictions between instruments. JWST, Ground-Based Observatory Arrays, Spectrometers. Imagine the JWST, the $10 billion jewel of infrared astronomy, turning its mirrors toward Comet Atlas. The observations come back, and they are clear carbon dioxide, water vapor, a gas-rich coma full of volatiles. The spectrometers are picking up molecular signatures, emission lines telling us that atoms are being excited, molecules are vibrating, gas is flowing outward from the nucleus. Meanwhile, ground-based optical telescopes are seeing asymmetry, or in some cases, seeing almost nothing at all. Different instruments, different stories. What is happening? The answer lies, in part, in what each instrument is actually measuring. The JWST operates in infrared wavelengths, looking at the wavelengths where molecules emit light as they vibrate and rotate. It is extremely sensitive to gas, to the chemical composition of whatever is floating around the nucleus. It doesn't need to see sunlight reflected to detect a coma. It's listening to the molecules singing in the infrared, and those songs are loud and clear. SphereX, another infrared mission, reported a large amount of vaporizing carbon dioxide around Atlas, with a carbon dioxide to water ratio that is unusual, even by the standards of strange comets. Optical telescopes are different. They are looking at reflected sunlight, at how dust particles scatter the sun's light back to us. To see structure in an optical image, you need extended dust. You need particles spread wide in space that can catch and redirect sunlight. If the dust is too compact, too close to the nucleus, or if the particles are the wrong size to scatter efficiently at optical wavelengths, you might not see much, even if gas is pouring off the object. This is where scattering functions come in. Small dust particles. Micrometer-sized particles scatter light effectively and can form a visible tail. Millimeter to centimeter-sized particles do not scatter well, and they move more slowly. They are harder to eject from the nucleus because they have more mass. These larger particles can linger near the object, creating a compact but optically faint shroud. That is difficult for optical telescopes to detect, but still produces a lot of gas, as ice sublimates from their surfaces. Then there is the phase angle geometry, the angle between the sun, the object, and the observer, which changes how we see any tail or coma structure. If we are looking at the object from the wrong angle, the tail can be foreshortened, pointing almost directly toward us or away from us, making it effectively invisible, even if it is there. Different instruments observing at different times, from different positions in their orbits, see the object from different angles. A tail visible to one instrument might be hidden from another, purely due to bad luck with the geometry we have seen before. Disagreements between instruments before. Comet Ison in 2013 was predicted to be spectacular and then disintegrated, but different telescopes reported different levels of activity at different times. See 2017. K2 showed a coma in some observations and looked quiet in others, sparking debates about whether it was truly active or just occasionally outgassing. The difference here is the scale. Atlas isn't just showing fluctuations. It's showing a twofold dichotomy. Either it has a tail or it doesn't. Either a point source or an extended object. There is very little middle ground in the observations. The timing mismatch makes things worse. JWST observes in certain windows, ground-based telescopes. In other windows, TESS has stared continuously, but at a lower spatial resolution. What if the object is intermittently active, releasing dust and gas in bursts rather than a steady stream? Then one telescope might catch it during an active phase, while another sees only silence. The observations would seem contradictory, even though both are reporting accurately what they were seeing at the time. But even when accounting for all of these effects, the level of disagreement was unusual. Deep stacking of optical images from professional observatories would have recovered faint dust features if they were there. Tests after stacking thousands of frames revealed nothing extended, suggesting that either the dust was extremely compact or it simply was not there, in the quantities we would expect. And if it was not there, where did all of that gas come from? Gas does not just appear. It comes from ice sublimating off of dust grains, or directly from the nucleus. Both processes should produce dust. You begin to wonder if you can trust any single instrument. Each instrument is seeing a part of the elephant, faithfully reporting what its particular sense detects, but the composite picture does not combine into anything coherent. This is how most astronomical mysteries are resolved. You collect more data, refine your models, and realize you are missing some subtle effect, like unexpected scattering properties or an unusual composition. But every time we added another observation of Atlas, the picture became more ambiguous instead of clearer. Part 3. The timeline and the pivot point, where Psyche fits in and where the public record falls silent. We have hit a wall with the telescopes on Earth and in space, all of them disagreeing on what they are seeing. Now, we need to talk about what may be the most important observation that has not been publicly discussed: the Psyche spacecraft, launched by NASA to study the metal-rich asteroid 16. Psyche has been traveling through interplanetary space with a suite of imaging instruments. Its mission is to reach its target asteroid, but along the way, it is equipped with cameras that regularly take images for calibration, navigational frames, and opportunistic science observations. The spacecraft carries an imager capable of capturing detailed images. During its cruise phase, mission teams regularly point these cameras at various targets to test the systems, calibrate the instruments, and gather additional science as opportunities arise. This is standard procedure for interplanetary missions. You have a camera. You are flying through space. You take pictures when you can. NASA has publicly released some of these images. Calibration images of the Earth and the Moon from various distances. Star fields to verify navigation. Things like that. This is where the timeline gets interesting. Based on public astronomical data, the positions and trajectories of Psyche and by Atlas, there were windows when the object from interstellar space would be within observation range. Potentially within range of the spacecraft's camera, not necessarily at close range, but close enough for a targeted observation to have potentially captured useful data. The precise geometry depends on orbital mechanics, which we can calculate from the mission parameters. These have been published. Yet, the possibility exists. So, where are those images NASA maintains archives of raw mission data? Most space missions eventually release their raw frames, or at least the metadata about what was imaged and when. These archives are how amateur astronomers sometimes discover comets or asteroids in old images, and how researchers go back and find things that were missed during the initial analysis. In principle, the raw images from Psyche's instruments should be findable, either in NASA's planetary data system or in mission-specific archives. The mystery is, there has been no public announcement about the release of the Psyche images showing by Atlas during its closest approach phases. This could mean many things, and we need to be careful about jumping to conclusions. Let's consider the innocuous explanations first, as they are perfectly plausible. Spacecraft data downlink is a limited resource. Deep space missions can only send back a certain amount of data. During each communication window with Earth, mission planners prioritize what gets transmitted. Engineering telemetry comes first, then science data from the primary mission targets, then everything else. If Psyche's camera did capture images of Bi-Atlas, those frames might be sitting in the spacecraft's onboard memory, scheduled to be downlinked during a future communication window. With bandwidth, there is also compression and data management to consider. Spacecraft do not have unlimited memory. They use ring buffers that overwrite old data. As new data comes in, if the Atlas images were not flagged as high priority, they could have been heavily compressed or even overwritten by later observations. This happens more often than the public realizes. Not every frame captured by a space mission makes it to Earth in full resolution. Metadata and indexing errors are another possibility. The images might exist in the archive, but not be cataloged correctly. Incorrect timestamps, mislabeled target fields, corrupted headers. Anyone who has ever worked with large astronomical databases knows how easily data can be effectively lost, just by being stored in the wrong place or with the wrong keywords. An image of Atlas could be sitting in an archive, labeled as a calibration frame or a star field, waiting for someone to realize what is actually in it. Then there is the bureaucratic explanation. Space agencies have embargo periods and data rights policies. With proprietary access windows for the mission team, it could simply be that the images exist. The mission team is analyzing them, and they will be released on a schedule that has not yet come. Science teams are often given priority to use their data before it is released to the public. This protects the people who designed and built the instruments, giving them time to publish their findings before others publish first using the same data. All of these explanations are plausible. None of them require a conspiracy or a cover-up. They are just the normal friction of how space missions operate. But here's the point. The absence of evidence is not evidence of absence. We do not know what was photographed because we cannot see the entire archive. We do not know what was prioritized for downlink, what was compressed, or how things were labeled. The metadata could tell us that, but it itself might be incomplete or inaccessible. What we can do, what we should do, is ask. Freedom of Information Act requests can compel the release of government-held data. Requests for archival access could be submitted for mission logs, observation logs, and equipment activity reports. These are documents that exist and can be requested. The question is whether the images that could solve the Atlas mystery are lying in some archive, waiting to be discovered, or whether they were never captured at all, or whether they were captured and are being withheld for reasons we do not yet understand. This is where the story could go in several directions. If the images exist and are released, we could finally see what Atlas truly looks like, resolving the contradictions between TESS and JWST and everything else. If they don't exist, we need to find out why a spacecraft with functioning cameras would not capture what could be the astronomical event of the decade. And if they exist but are inaccessible, then we have an entirely different kind of problem, one that raises questions about transparency and data governance in space archives. Part 4. Alternative physical hypotheses to a comet. Non-comet hypotheses that fit the data. Let's step back from the difficult archival question and ask something more fundamental. What if Atlas was not a comet in any conventional sense? What if we've been trying to put it in the wrong category all along? If this object doesn't follow the rules for comets, then what else could it be? And is there an alternative explanation that can actually survive all the constraints we've piled on? Hypothesis 1. A large, inert object with minimal outgassing. Imagine a block of rock and ice from another star system, forged by different formation conditions than anything in our solar system. Perhaps it is mostly inert, not sublimating vigorously like a comet, but still releasing small amounts of gas through fissures, through rare pockets of volatile ice exposed on its surface. This would explain the gas signatures seen by JWST without requiring the large dust production that would create a visible tail. The object would remain compact, appearing as a point source, yet still show chemical activity. The problem with this model is quantifying the gas production rate. JWST's measurements indicate significant volatile loss. You can't hide that much. Gas production in minimal fissures without ejecting rock and dust. Sublimation is not a clean process. It would pull the dust particles along as it vaporizes. You would need a very specific component, perhaps a pure volatile, somehow separated from the dust, and that does not seem geologically plausible. Hypothesis 2. A debris cloud. What if Atlas is not a single object, but rather a swarm of smaller, tightly bound fragments, all moving together, individually too small to resolve, even with our best telescopes, but collectively creating the brightness that we measure? Think of it like a school of fish or a flock of birds, where the group behaves as a single unit. Each fragment produces a little gas and a little dust, but the material remains confined within the swarm. Instead of flowing outward into a classic tail, this could explain its appearance as a point-like source. If the fragments are close enough together, closer than our angular resolution can separate them, we would see them as a single object. Gas production would be distributed over many small surfaces, rather than coming from a single nucleus, potentially creating different scattering properties from what we would expect. But this model has problems too. Why would the fragments stay bound together? They would need some kind of collective gravity, or they would drift apart from each other over interstellar distances, and a swarm would show some structural fluctuations, some elongation or fuzziness, even if we could not resolve the individuals. Hypothesis 3. Electrodynamic effects. This is where things get strange. Suppose the dust particles around Atlas are electrically charged, and there is a magnetic field, or an electric field strong enough to hold them near the nucleus. Charged dust can levitate and be trapped in configurations that do not follow simple ballistic trajectories. We see this in planetary rings, in plasma experiments, in the lab, in regions where electromagnetic forces dominate over gravity. If Atlas carries an electric charge, if it is generating fields through some process we do not understand, then the dust might not escape into a tail at all. It could levitate, circulate, and be confined. The gas would still escape, because molecules are harder to trap electromagnetically. but the dust would stay put, invisible, to optical telescopes looking for an extended structure. This would explain almost everything: the compact appearance, the detection of gas, the lack of a visible tail. The problem is, we have no mechanism for how an inert object could generate the necessary fields. You would need something active, something that is generating energy. And that brings us to Hypothesis 4, the hypothesis that makes scientists uncomfortable, but one we must at least consider, given how strange everything is. What if this object is artificial? What if it was engineered, carrying active systems that produce the signatures we are measuring, through technological processes, rather than geological ones? An artificial object could perfectly explain the contradictions. Active reflectors could create the brightness variations, and energy sources could produce gas emissions, without the need for sublimation, allowing for a clean appearance. For a manufactured structure, electromagnetic signatures, if we were to find them, would be expected, not a mystery. The problem, of course, is that this is an extraordinary claim requiring extraordinary evidence, and we do not have that evidence. We have anomalies, contradictions, and unexplained observations, but that is not proof. Each of these models makes hypothetical predictions. The micro-outgassing model predicts that we would eventually see some dust production, faint but detectable, if we stack enough observations. The debris cloud model predicts structural variations over time, as the swarm evolves. The electromagnetic model predicts that we would find field signatures, polarization anomalies, perhaps radio waves. The artificial model predicts things that do not occur naturally, such as geometric structures, spectral lines from industrial processes, and temporal patterns that show control rather than chaos. What is noteworthy is that none of these models is a perfect fit. Each model explains some observations, while raising new questions about others. The natural explanations require components, or unlikely configurations. The more exotic natural explanations require physics that we have never observed in comets before, and the artificial explanation requires us to accept that we are looking at technology from another civilization. That is a leap that most scientists are unwilling to make, without overwhelming evidence. But we will need one of these explanations, or something even stranger, because the standard comet model has been broken. We can't just keep saying it's a comet, when at a certain point, it refuses to behave like one. If an object constantly violates your expectations, you must update your model of what that object is. We might be at that point with Atlas. Part 5. Formalizing the challenge. What would convincingly prove a non-natural origin? Let's draw a line. Let's establish precisely what needs to be proven to disprove the natural explanation, and force us to seriously consider that we are looking at something artificial. This is no longer about speculation. This is about defining verifiable criteria that would satisfy even skeptical scientists. Criterion 1. A resolved structure inconsistent with known physics. If we could capture an image of Atlas with high enough resolution to see its shape, and that shape showed sharp edges, right angles, symmetrical patterns, or moving parts, that would be very significant. Natural objects are lumpy and irregular, shaped by accretion, impacts, and gravity. They do not create geometric precision. A spherical object isn't suspicious, as spheres minimize surface energy, but a cube, a cylinder, articulated components moving relative to each other, those things would require an explanation. Criterion 2. Clear spectral lines from compounds that don't belong. Comets show water, carbon dioxide, carbon monoxide, and organic molecules, all things we expect from primordial matter. If a spectrometer revealed technetium, which only exists as a product of nuclear reactions, or if we saw industrial compounds, synthetic polymers, or isotopic ratios that do not occur naturally, that would be a cosmic red flag. The universe creates a palette of limited chemicals through stellar nucleosynthesis and chemistry. Anything outside that palette needs to be explained. Criterion 3. Multiband registration anomalies. Imaging at different wavelength bands, and overlaying them. Natural objects show. Models can predict hotspots emitting more infrared radiation than scattered dust, or gas emitting optical light at specific wavelengths. If the images in different frequency bands do not physically align, meaning they should, then if a structure in one band does not correspond to anything in the other bands, that indicates something more complex than simple thermal and scattering processes. Criterion 4. Metadata and telemetry signatures. This is about data provenance. If spacecraft observations exist, the raw frames must have headers with timestamps, instrument settings, data checksums, and calibrations. These headers can be verified by cross-checking with the mission logs. Inconsistencies here could indicate manipulation, but more importantly, the presence of consistent metadata can verify and reinforce any claims about what was observed. You cannot prove something extraordinary with data that you cannot validate. Criterion 5. Correlated signals across different physical domains. If Atlas shows an optical brightening, a TX radio burst, and a neutrino detection, all simultaneously time-locked to the same event, that would be very noteworthy. Natural processes can produce multi-wavelength emissions, but the correlations follow patterns that we understand. Blazars, pulsars, supernovae, these have characteristic signatures. Something completely novel in its multi-wavelength behavior would require a new explanation. History provides us with examples of how data quality and provenance can make or break extraordinary claims. The data tapes from the Apollo program were nearly lost, requiring recovery efforts many decades later. Some were overwritten. Some degraded. Astronomical archives have had their own issues. Mislabeled data, degraded storage media, institutional knowledge lost when key people retire. The quality of the evidence matters as much as the evidence itself. There is also a sociology to it. Mission teams face immense pressure. Careers depend on successful missions, on publishable results, and on not making claims that they cannot defend. National interests play a role. Some data may be classified or embargoed for strategic reasons that have nothing to do with scientific merit. The fear of ridicule is real. No scientist wants to be the one to declare the existence of aliens and be wrong. The professional cost is too high. So, what would a reliable dataset look like? Raw, uncompressed frames, neither processed nor enhanced, full metadata headers that can be verified, and based on independent sources, with checksums to prove the data hasn't been altered. Multiple, independent observations from different instruments, corroborating each other. Open access, so that anyone can analyze the data and attempt to reproduce the findings, and ideally, a documented chain of custody from capture through storage, to release for any video, any claim, any announcement about Atlas. That must be held to these standards. If someone says that, they have spacecraft imagery that shows something extraordinary. The first question has to be, where are the raw frames? Can we verify the metadata? Can independent analysts access the data? Without that level of transparency, we are just looking at another ambiguous observation that raises more questions than it answers. The burden of proof for an extraordinary claim is immense, and it should be. Science has progressed by being rigorous about evidence, by demanding reproducibility, by not accepting claims just because they are fascinating. But science has also progressed by following up on anomalies, by taking observations that don't fit seriously, by being willing to update models when the data demands it. We are at a moment where the Atlas observations are strange enough to warrant serious attention, but not yet clear enough to draw firm conclusions. What happens next depends on whether we can gain access to decisive observations, whether new data will narrow the gaps in our understanding or widen them, and whether the scientific community can balance healthy skepticism with genuine curiosity. The framework is in place. The criteria are defined. Now we wait to see if the evidence will emerge. J 1.832, a 44-minute pulse in radio and X-rays. Let's zoom out from Atlas a bit and look at something happening in our galaxy that is forcing astronomers to question what they thought they knew about cosmic objects. Astronomers using the Australian Square Kilometre Array, Pathfinder, and NASA's Chandra X-ray Observatory have discovered an object called ASCAP J 1732-0911. It pulses like a heartbeat every 44 minutes, in both radio waves and X-rays simultaneously. This discovery came as part of a survey searching for radio sources that are transient, objects that appear and disappear or fluctuate in brightness over time. Long-period transients, or LPTs, are a relatively new class of astronomical object, flashing at radio wavelengths every 10 minutes to several hours. They are rare, poorly understood, and do not fit neatly into any existing classifications. ASCAP J 1732-0911 is the first one observed to pulse in X-rays, as well as radio waves. This makes it uniquely strange. The data is precise. The object emits a 2-minute-long burst of radio waves, then goes quiet for 42 minutes, then bursts again. The cycle repeats with clockwork regularity. Chandra observations show. The X-ray pulses are synchronized with the radio bursts, not perfectly overlapping, but definitely correlated. The object is located about 15,000 light-years away, somewhere in our galaxy, but not within any obvious star association or nebula. What could produce such a signal? The immediate suspects are all magnetically active objects. Magnetars are neutron stars with extremely powerful magnetic fields, and they are known to pulse, but magnetar pulses are typically much faster, milliseconds to seconds, not 44 minutes. You would need a novel configuration, some reason for the field to store energy slowly and release it periodically, and no one has a convincing model for that yet. Highly magnetized white dwarfs are another possibility. These are dead stellar cores that have collapsed to about the size of Earth, but are still spinning and maintain strong magnetic fields. If you have a white dwarf spinning with a 44-minute period, which is unusually slow, and if it has active accretion or magnetic reconnection events, synchronized with its rotation, you could get periodic pulses. But then again, the timing is strange. Most white dwarfs either spin much faster or have lost their magnetic fields entirely. Binary systems offer another explanation. If you have two objects orbiting each other with a 44-minute period, and some interaction between them, perhaps accretion or tidal heating, creates periodic outbursts that could explain the observations. The problem is, a 44-minute orbital period implies that the objects are very close together, close enough that they should have already merged, or are rapidly spiraling inward due to the emission of gravitational waves. No standard model is satisfying. Each model requires tweaking parameters, invoking special conditions, and explaining away inconvenient observations. And this is before we even try to connect it to Atlas, which on the surface seems impossible. ASCAP J 1.832 is a galactic object, probably stellar in nature, pulsing in radio and X-rays. Atlas is an object from interstellar space, showing optical and infrared anomalies, but with no confirmed radio or X-ray detections. They are completely different types of phenomena in completely different contexts. But here is why I bring it up. If an object in our galaxy can break all existing models, can produce a signal that doesn't fit with any known class of astronomical object, then we should be humble about declaring what is possible and impossible for other strange objects we encounter. ASCAP J 1.832 is proof that the universe still has tricks up its sleeve, mechanisms we don't understand, and classes of objects we haven't yet discovered. This discovery also highlights how much we are missing. ASCAP is a relatively new radio telescope, only operational for a few years. Chandra has been operational since 1999, but can only observe what we pointed at. ASCAP J 1.832 has probably been pulsing for thousands or millions of years, and we are only just now noticing how many other strange objects are out there, detectable with current technology but not yet found, because we haven't looked in the right place or in the right way. This relates to Atlas, because it changes the empirical probabilities. Before ASCAP J 1.832, you might have said that strange periodic signals across multiple frequency bands are not something that natural objects do. Therefore, any claim of such signals was probably an instrumental error or a misinterpretation. Now we know such signals exist, and we don't have a good explanation for them. That should make us more cautious about dismissing anomalies in other objects, just because they don't fit with existing models. It also suggests a research strategy. When you find one anomaly, you should look for others and see if patterns emerge. Maybe there's a connection, maybe not, but you won't know unless you look. That brings us to the question whether Atlas and ASCAP J 1.832 could be related by some common physics. That might sound absurd, but let's at least explore it before dismissing it. Part 7. Cross connections. ASCAP J 1.832 and Atlas. Are they related by any plausible physics? We need to be clear from the outset. There is no evidence that ASCAP J 1.832 and Atlas are related in any way. They are different types of objects, different scales, different contexts. What we are doing here is exploring analogies, searching for potential common mechanisms, asking if the same strange physics could be at work in different regimes. Even if the answer is no, thinking about it is illuminating. It illuminates what experiments we should conduct. Starting with energy scales. ASCAP J 1.832 is producing radio pulses. The radio emission could come from synchrotron radiation, where charged particles spiral in a magnetic field, or from coherent plasma processes. X-rays require higher energies, hot plasma, magnetic reconnection, particle acceleration to relativistic speeds. These are energetic processes, much higher energy than anything we associate with comets, which are just ice and rock heated by the sun. But what if Atlas were carrying or generating a magnetic field? Comets have induced magnetospheres. When the solar wind interacts with their comas, the interaction is weak, unlike the organized fields in a magnetar or an accretion system. But it exists. What if Atlas had an unusually strong internal field? Or if it were carrying charged particles that generated field structures? Could those fields produce radio emission under the right conditions? Plasma physics gives us some possibilities. Coherent radio emission can come from plasma instabilities, from regions where the density of charged particles fluctuates strongly, from boundary layers where different plasmas interact. If Atlas is outgassing, that gas would be ionized by solar UV rays. An ionized coma is a plasma, and plasmas can support waves, instabilities, emission mechanism. Most of the time, these are too faint to detect. But under special conditions, perhaps extremely high charge densities, or unusual magnetic configurations, you could get detectable signals. However, the timing is completely different. ASCAP J1736 pulses every 44 minutes. With precise regularity, that regularity suggests rotation, orbital motion, or some kind of resonant oscillation. Atlas, however, does not show that kind of periodicity. In its optical observations, if there is periodic behavior, it is on different timescales, days or weeks rather than minutes. So, any common mechanism would have to operate over a wide range of characteristic times. This seems unlikely, unless there is a common underlying process that scales differently in different environments. What about X-rays? X-ray emission from comets has been detected before. It is generated when solar wind ions exchange charge. With neutral atoms in the coma, it's faint, requiring sensitive instruments to detect, but it is real. If Atlas had an unusually dense or active coma, the X-ray emission would not be surprising. The question is whether that X-ray emission is periodic, structured, or synchronized with anything else we are observing. Charge exchange is naturally quite uniform, not pulsed. Let's consider a speculative, unifying hypothesis. Just as a thought experiment, suppose a natural class of objects exists that maintain strong, localized magnetic fields and a dense plasma environment. In a galactic context with stellar mass scales and compact objects, you get ASCAP J1736, periodic pulses from rotation or oscillation, radio and X-ray emission from plasma processes. In an interstellar context, with a much smaller object like Atlas, the same field and plasma physics are at play, but manifest as a confined coma, an unusual gas-to-dust ratio, and perhaps radio bursts that are too faint or brief to be detected. This hypothesis makes testable predictions. If Atlas and ASCAP J1736 share a fundamental physics, we should look for faint radio pulses from Atlas, especially during its perihelion phase, when the solar wind interaction that drives the outbursts is at its strongest, correlating with increases in optical brightness or gas production events. Polarization signatures in Atlas's scattered light suggest an organized magnetic field. Faraday rotation of radio sources should be seen through Atlas's coma. This would reveal the magnetic field strength, helping to correlate a neutrino detection with one of the two objects. If acceleration mechanisms are creating high-energy particles, most of these observations have not yet been performed or reported. Radio telescopes have not systematically monitored Atlas at high-time resolution. X-ray observatories may not have been pointed at it during its active phases. The data to confirm or rule out the connection may simply not exist yet. The comparison is useful, even if the answer is negative. For instance, if we observe Atlas at radio wavelengths during its next active cycle and see nothing, that result constrains the models. It tells us there is no coherent plasma emission, no synchrotron radiation, and no radio-generating mechanisms are at work. That is valuable information, as it eliminates hypotheses. And if we do find radio pulses or X-ray correlations, or any of the signatures we are predicting, that would be extraordinary. It would show that Atlas is doing something outside the normal behavior of a comet, something that connects it to active stellar objects like ASCAP J1.832. That would push us firmly into strange territory, where conventional explanations no longer hold, and we would have to start seriously considering alternative hypotheses that we would rather not think about. The point is, the anomalies in one object can inform how we think about anomalies in another. Patterns emerge when you make comparisons between different phenomena, and sometimes the most seemingly crazy connections turn out to be true, because nature uses the same physics in different contexts. We won't know until we look. Part 8. The 220 peta-electron-volt ghost particle. Why does a single neutrino matter? A single particle that changed everything, on a day that should have been unremarkable, deep beneath the Mediterranean Sea. A detector array called KM3-NET has recorded something that seemingly shouldn't exist. According to our conventional understanding of cosmic ray physics, a neutrino with an energy of 220 peta-electron volts passed through the detector, leaving behind a trail of light that tells a story about the most violent processes in the universe. Let me explain what that means, because the numbers at this scale lose their intuitive weight. 1 peta-electron volt is 1 quadrillion electron volts. The protons in the Large Hadron Collider, the most powerful particle accelerator ever built by humans, reach energies of about 14 trillion electron volts. This neutrino was carrying an energy 16,000 times greater than those protons. It is a cosmic bullet, fired by something so powerful. We do not have a complete theory for how it works. Neutrinos are ghost particles. They pass through normal matter as if it isn't even there. Right now, billions of neutrinos from the sun are passing through your body, through the Earth, and continuing on into space without interacting with a single atom. They have almost no mass, no electric charge, and no properties that allow them to bump into ordinary matter. Detecting them requires huge volumes of transparent material, like ice or water, instrumented with sensors that watch for the rare occasions when a neutrino interacts, creating a charged particle that emits light. As it travels faster than light can move through that medium. KM3 NEAT operates in the Mediterranean Sea, using the sea itself as its detector volume. Arrays of light sensors, suspended on cables, monitor cubic kilometers of water for the telltale flashes of light, of Cherenkov radiation, signaling a neutrino interaction. The ARCA component detected this particular event, seeing the characteristic pattern of a muon and working backwards through the physics to determine that the neutrino must have had at least 220 peta electron volts of energy. The analysis was confirmed. This was not a glitch or a misidentification. It was real. Why is this important? Because neutrinos. At these energies point to cosmic accelerators operating on scales that we can barely comprehend. The strongest candidates are blazars, supermassive black holes at the centers of active galaxies, accreting matter and launching jets of plasma at nearly the speed of light. Those jets can accelerate protons to immense energies, and when those protons collide with photons, or surrounding matter, they create pions that decay into neutrinos. Gamma-ray bursts, the death cries of massive stars collapsing into black holes, are another possibility. Anything that can accelerate particles to these energies is operating at the very extremes of physics. Now, here's the connection. Tenuous, but worth exploring. Could Atlas have been embedded in, passed through, or somehow connected to a high-energy astrophysical environment? The object came from interstellar space. We know its approximate trajectory. We can trace it back into the galaxy, but we don't know what it encountered on its journey. Did it pass through a supernova remnant, near a pulsar wind nebula, through regions of space where magnetic fields or plasma densities create particle acceleration zones? The speculation goes further. If Atlas were carrying exotic matter, fields we don't understand, or possessing properties we haven't yet detected, could it interact with the solar wind or the interplanetary medium in ways that generate high-energy particles? Could it be seeding neutrino production through mechanisms that are not active in normal comets? This sounds far-fetched until you remember that we don't really know what Atlas is. We call it a comet because it's in our solar system and shows some volatile activity, but everything about it is unusual. A concrete test exists: neutrino detectors like KM3 NET, IceCube at the South Pole, and other detectors maintain continuous monitoring. Their data is time-stamped and directionally resolved. If a high-energy neutrino burst occurred, coinciding with the perihelion passage of Atlas, or with its active phases, or with any of the unusual behaviors that we observed optically or spectroscopically, that correlation would be significant. The chances of a random coincidence can be calculated. If the correlation is strong enough, it suggests a physical connection. This has been done before with other astrophysical phenomena. When IceCube detected neutrinos from the direction of a known blazar during an active phase, it confirmed that blazars are indeed sources of neutrinos, a breakthrough in the multi-messenger astronomy revolution, based on correlating signals across different types of particles and radiation: light, neutrinos, gravitational waves. Each messenger tells you something different about the source, because each messenger is created by different physics, and travels through space differently. Neutrinos are special because they are very difficult to stop. If a source is creating them, they will escape directly, carrying information about whatever process is creating them. Gamma rays can be absorbed by dust or gas. Radio waves can be scattered, but neutrinos punch through everything and arrive at Earth pointing directly back to their source. They are the ultimate cosmic messengers for looking into environments that are otherwise opaque. The detection of a 220 peta electron subgisische esospicinet volt particle is proof that such messengers are out there, that we live in a universe with violent and powerful processes, enough to create them. It's a reminder that our census of cosmic phenomena is incomplete. We don't know all the ways nature can accelerate particles, create fields, and generate high-energy radiation. New classes of objects and new mechanisms are still being discovered. So, when we look at Atlas, with all its contradictions and anomalies, we should remember that the universe has shown us it can do things we don't predict. ASCAP J 1.832 pulses in ways that no model fully explains. A neutrino with unimaginable energy arrived from out there. Black holes merge and create gravitational waves that we only learned how to detect a decade ago. The list of cosmic oddities keeps growing. Perhaps Atlas is just a comet with an unusual composition, and we're overthinking it. But perhaps it's another entry in the catalog of things we didn't expect. Another phenomenon that will require new physics, or new categories to explain. The only way to find out is to keep observing, to keep correlating, to keep asking if different anomalies might be connected. And to do that effectively, we need access to all the data, including observations, that might be sitting in archives waiting to be analyzed. Part 9. The Impact of Space Weather, 4 CMEs, Aurora Forecasts, and Why the Environment Matters when we've been focused on distant objects, and strange particles, something much closer to home, has made life complicated for observers. The Sun has been remarkably active, with 4 coronal mass ejections, launched towards Earth in quick succession, expected to arrive between October 15th and 17th, 2025. These are clouds of magnetized plasma weighing billions of tons, ejected from the Sun's corona, traveling through space at speeds of millions of kilometers per hour. And when they strike Earth's magnetic field, they cause geomagnetic storms. For aurora watchers, this is exciting news. Geomagnetic storms push charged particles into Earth's upper atmosphere, near the poles, where they collide with atmospheric gases and create shimmering curtains of light that we call auroras. The stronger the storm, the farther from the poles the auroras can be seen. These 4 CMEs have prompted forecasts of major auroral displays, potentially visible at mid-latitudes. For astronomers trying to observe faint objects like Beidou Atlas, space weather is a nightmare. The same charged particles that create beautiful auroras also create interference. Radio observations are contaminated by ionospheric scintillation, where fluctuations in the ionized upper atmosphere cause signals to twinkle and fade, much like twinkling stars. But worse, increased cosmic ray showers strike detectors with false signals. Optical observations can be affected by airglow, where excited atmospheric molecules emit light, adding background noise to images. Spacecraft instruments face direct effects. Solar energetic particles can cause bit flips in electronics, corrupting data or triggering false detections. Star trackers, used for spacecraft attitude control, can be confused by high-energy particles, striking their sensors and creating false stars. Camera sensors can show noise spikes, hot pixels, and streaks from cosmic ray hits. All of this must be filtered out during data processing, and sometimes the filtering is imperfect. This is where it gets insidious. Space weather creates plausible deniability for data problems. If frames are missing from an archive, if images show unexpected artifacts, if telemetry has gaps, you can always blame space weather. a cosmic ray strike in that observation window, a solar energetic particle event corrupting data, a spacecraft having to enter safe mode because of a storm. All of these are legitimate effects that really happen, but they are also convenient excuses. How do you distinguish between genuine space weather impacts and other reasons why data might be incomplete or problematic? You look at the details. Space weather effects leave behind specific signatures. Cosmic ray hits appear as sharp spikes in single pixels or small clusters. Ionospheric scintillation shows characteristic timescales and frequency dependencies. A spacecraft's safe mode generates specific telemetry patterns and log entries. If you have access to the full metadata, you can usually tell what happened. The problem is when you don't have access, if all you are told is that data was lost due to space weather, without seeing the detailed logs, instrument diagnostics, or the pre- and post-calibration arcs, you can't verify the claim. It might be true. It might be a simplification of a more complex situation. Or it could be covering up something else entirely. This is not paranoia. This is how data integrity works. Scientific claims require verifiable evidence, and evidence requires provenance. You need to know where the data came from, how it was processed, and what happened to it along the way. When gaps appear in that chain of custody, when explanations are vague or incomplete, the data becomes less reliable. For making strong claims, whether those claims are mundane or extraordinary, historical examples abound. The cooling system of the NICMOS instrument on the Hubble Space Telescope failed and was initially blamed on generic thermal problems. But it turned out to involve specific mechanical issues that took years to fully diagnose. The Mars Observer probe was lost during orbital insertion, with telemetry suggesting a fuel line rupture, but the incomplete data left room for alternative theories. When data is incomplete, explanations remain ambiguous. For the Atlas observations, this matters because we are relying on a patchwork of instruments, each with its own vulnerabilities. To environmental effects, the ground-based telescopes battle through atmospheric turbulence and weather. Space telescopes contend with radiation and thermal cycles, and radio arrays deal with ionospheric conditions. If all of these instruments show slightly different results, how much is due to real physical differences in what they are observing versus instrumental and environmental effects? 4 CMEs arriving this week add another layer of complexity. Any observation in this window will have to account for the enhanced background, potential instrumental effects, and calibration uncertainties. This does not make the observations worthless, but it means larger error bars. And larger error bars mean greater ambiguity about what is really happening with Atlas. There is also a question of timing, which makes me wonder if definitive spacecraft observations of Atlas exist. If there are frames that would resolve the contradictions we have discussed, why have they not been released during a week when space weather provides a ready explanation? For any delays or data issues, it would be the perfect time to say, "We wanted to release this sooner, but the CME complicated our data processing. Here is what we have." The absence of such an announcement is notable, though not necessarily significant. Space weather is a part of the structural blindness we face when trying to understand cosmic phenomena. The environment between us and the object, between the instrument and the data archive, and between observation and publication introduces noise, gaps, and uncertainty. Some of this is unavoidable physics, some is technological limitation, and some may be organizational or procedural. The way data is processed and released by institutions with their own priorities and constraints. To overcome this blindness, we need redundancy, multiple instruments, multiple observation strategies, and multiple independent analyses of the same data. We need transparency about what is being observed and when, about data quality flags, about processing pipelines, and we need a culture where questioning data provenance is not seen as adversarial, but is essential to doing good science. Part 10. Biased Instruments and Archives. Our Structural Blindness. This process is unglamorous and technical. It determines what we can actually know about the universe. And it is rife with places where information can be lost or corrupted, or are simply never released. It all begins at the detector. A photon arrives, depositing its energy, creating a signal. That signal is converted into a digital value, a number representing the brightness at a specific pixel at a specific moment in time. Immediately, you've lost information. The conversion has noise, quantization errors, sensitivity variations across the detector, cosmic rays, and charged particles constantly strike the sensor, creating false signals that must be identified and removed. Hot pixels, dead pixels, and optical defects all create patterns in the data that are not astrophysical. Next is compression. The raw detector frames are very large. A single high-resolution image can be hundreds of megabytes. A spacecraft can generate thousands of frames in a single observation campaign. There isn't enough bandwidth to send all of that data back to Earth uncompressed. So, it gets compressed. Sometimes this is lossless compression, which preserves all the information. Other times, it's lossy compression, which discards details considered less important. The choice of what to compress and by how much affects what science can be extracted later on. Then there is the issue of the buffer. Spacecraft have finite memory. They cannot store everything forever. Data is written to memory and held there until it can be downlinked. Then it is often overwritten by new data. If something interesting happens but isn't flagged as a high priority, if the window of observation closes before the data is transmitted, those frames may never reach Earth. They are gone, overwritten, irretrievable. Downlink scheduling is another bottleneck. Time on the Deep Space Network is precious. Every spacecraft, every mission, competes for the communication facilities. When a spacecraft gets a slot to transmit, it sends what mission control has prioritized. Engineering telemetry first, to ensure the spacecraft is healthy. Then primary science data. Then secondary science. Calibration frames. Supplementary observations. In whatever order the mission team has decided. If the object you're interested in is considered a low priority, its data might have to wait weeks or months to be downlinked. Once the data reaches Earth, it enters the archival pipeline. This involves significant processing, as the raw frames are converted into standard formats. The headers are filled with metadata, such as target coordinates, observation time, exposure duration, filter settings, and instrument quality. This metadata is crucial because it's how you search the archive later. Incorrectly labeled metadata means the data becomes effectively lost, even though it physically exists in the archive. Archives are reorganized and migrated to new storage systems, and re-indexed as software evolves. Each migration is an opportunity for file corruption, checksum errors, and broken links between data and metadata. Large archives with millions or billions of files are almost guaranteed to have a portion that is corrupted, mislabeled, or inaccessible due to technical glitches. Then there are embargo periods and proprietary data rights. Mission teams often have exclusive access to their data for months or years before public release. This protects the scientists who built the instruments and designed the observations, giving them time to analyze and publish before others can scoop their results. It's a reasonable policy, but it means that potentially interesting data can sit in restricted archives, known only to a small group, unavailable to the wider community for independent verification of any delays. Bureaucracy exacerbates these problems. Releasing data requires resources. Someone must prepare the files, write documentation, verify quality, and set up access systems. Space agencies and observatories are often understaffed and overworked, so data release schedules slip, and low-priority observations, can get backlogged in internal archives simply because no one has the time to process and release them properly. There are historical examples of important data being recovered from archives years after it was collected. Reanalysis of archival Hubble images has revealed objects missed during initial processing. Voyager data, found in storage many decades later, preserved observations that were thought to be lost. Amateur astronomers have found comets and asteroids in images publicly released that professionals had overlooked. The challenge of archiving is immense, and no one can systematically check every frame of every observation. This structural blindness affects all of astronomy, not just Atlas. We are only seeing the subset of the observed universe that is successfully downlinked, properly stored and labeled, and analyzed by someone with the interest and resources to do so. The universe is effectively filtered through this process, and we don't know what we're missing. For Atlas in particular, this means a few things. First, the discrepancies between instruments may partly reflect these procedural effects. TESS doesn't see an extended coma because its data processing is optimized for point sources. Ground-based telescopes, on the other hand, might miss faint tails because their data reduction process assumes point sources. JWST sees gas because its spectrometer is extremely sensitive to molecular emission, but it doesn't perform the wide-field imaging that would reveal the dust structure. Second, the absence of images of Psyche in public archives can be explained by any of a dozen procedural failures or delays, none of which requires a conspiracy.
Or perhaps an oversight. Yet explaining this absence does little to soothe the sense of unease it brings. If these observations do exist, it seems only natural that they should be available for us to gently examine. And if they do not, we should be allowed to understand why these precious windows of observation were missed. A certain clarity about the process is, in its own way, just as important as the data itself. And thirdly, this line of thought gently suggests a strategy for our research. For anyone who wishes to understand Atlas, or other quiet anomalies like it, it may be helpful to look beyond the published results or the official announcements, to delve quietly into the archives and download the raw frames, should they be available, and then to reprocess them with different assumptions, searching for the subtle inconsistencies in the metadata. These could reveal observations that have been mislabeled. By comparing the observation logs with the data that was actually stored. To find these differences, one might send gentle requests for access and information to encourage these institutions toward greater openness. And here, citizen science has a quiet but important role to play. Amateur astronomers and data scientists, who are often free from institutional pressures or concerns about their careers, can feel free to ask the quiet questions. And they can pursue lines of analysis that professionals might shy away from, collaborating gently across different communities, sharing their data, their methods. After all, the history of astronomy is filled with important contributions from such dedicated amateurs. And our digital era makes this kind of gentle participation easier than it has ever been. This idea of structural blindness, it is a real thing, but it is not something that cannot be overcome. It simply asks for a quiet persistence. It requires technical skill and a willingness to gently navigate the bureaucracy. It asks that we build connections, alliances of people who care enough to find the answers, to do the patient, humble work of data archaeology. And it asks that we maintain a gentle pressure on the institutions, encouraging them to improve their data processes, their release schedules, and their overall transparency, because, in the end, the data does exist. A photon of light gently strikes a detector. A signal is recorded. The bits of information are stored. The question then becomes, can we access them? Can we verify them and study them openly? This is a question as much about policy and priorities as it is about physics. Part 11. The data hunt. So, let's consider the specific, careful actions we might take right now. We cannot simply wonder and wait for others to provide the answers. Here, step by step, is precisely what could be done to gently search for the data that might finally resolve the quiet mystery of Atlas. Here is a gentle path for any determined mind to follow. First, we must identify the precise observation window. We need to calculate the exact coordinated universal time when the asteroid, Atlas, would be within the potential field of view of the Psyche spacecraft. This requires astronomical data for both of the two bodies. This data is publicly available from JPL Horizons and other such sources. The Horizon system provides the precise position and velocity data for objects in the solar system at any requested moment in time. It accounts for gravitational disturbances and observational geometry, calculating the angular separation to find a favorable viewing window. This simply means we are determining when Atlas and Psyche are both positioned so that the spacecraft's instruments can observe the object. Considering factors such as the sun angle, this angle affects both the object's illumination and whether the sensitive sensors can be pointed in certain directions without any risk. We must also consider the spacecraft's attitude constraints and its various operational modes during different phases of the mission to identify the specific dates and times. This is when Psyche's cameras might have been aimed toward Atlas, either intentionally or as part of routine monitoring. The spacecraft often conducts optical navigation imaging, calibration sequences, or engineering tests that scan across fields of the sky. Atlas could have appeared in these observations, even if it was not the intended target. The analysis of this window should extend from the time of Psyche's launch to the present day, with special attention given to times when Atlas was bright or in a favorable observational geometry. Second, we must identify the instrument specifications and their data products. Psyche carries specific cameras, each with a known field of view, sensitivity, and set of operational modes. These specifications are published in the mission's documentation, often within the instrument manuals, mission design documents, and technical reports available through the NASA Technical Reports Server, or the official mission websites. The specifications for the spacecraft's imaging instruments include details such as the pixel scale and spectral response, as well as readout noise characteristics and typical exposure parameters. This helps determine what those instruments are capable of detecting at what limiting magnitudes and with which exposure times. This, in turn, requires us to calculate the expected brightness of Atlas at various times, taking into account its distance from both the Sun and Psyche, as well as its phase angle, and any activity that might enhance or diminish its visibility. Then, we compare these predictions with the camera's recorded sensitivity limits to determine if Atlas was bright enough and close enough to create a useful image. This establishes whether an observation was truly feasible, not just geometrically possible. A faint object in a wide field might be detectable with a long exposure time, but it could be invisible in short engineering frames. Conversely, a bright object might saturate the detector if the exposure time was not properly adjusted. Understanding these technical constraints helps us know what kind of data to expect and what might have been missed. Thirdly, we begin a systematic search of existing archives, like NASA's Planetary Data System, which stores data from planetary missions. The archive structure is standardized, but it is not always intuitive. With data organized by mission, by instrument, and by observation time, using specific naming conventions that differ from one mission to the next. The PDS uses a hierarchical directory structure, where understanding the organizational logic is essential for an effective search. We search by the instrument's name, by observation date ranges, which include the windows we identified earlier, and by the target's coordinates, downloading image indices, and metadata, catalogs that are available. These indices contain summary information about each observation, without requiring us to download the full image files, which makes these systematic searches computationally possible. We use automated scripts to search for file names, headers, or comments that mention Atlas or other interstellar objects, or even calibration targets, or perhaps even chance observations of a neutral field that happen to include the correct coordinates. Python libraries like AstroP and Planetary Data Reader can parse these PDS formats and help automate the search across thousands of files. Regular expressions can help match the different naming schemes that might reference the object. This search of the archives must be very thorough. We don't just look for the obvious matches. We also check engineering data products and calibration frames, and even rejected observations that may have been left out of the main science archives. Sometimes the most interesting data is hidden away in supplementary collections, or in data that was flagged as being of poor quality. Fourthly, we can file formal data requests if the search of the archives does not yield results. We would submit Freedom of Information Act requests for the observations. To be specific, it is best to request all of the raw image frames from the Seiki cameras. This should include those from the calculated observation facilities, along with the device log metadata and any accompanying data quality assessments. Specificity is quite important in these information requests, as vague inquiries often receive vague responses or encounter delays. This happens while the agencies take the time to seek further clarification, and these requests must always be responded to, although the response may be delayed or it may claim certain exemptions, with common ones including matters of national security. Other exemptions might be proprietary information or data that has not yet completed its standard processing. Even a denial can provide useful information, as it may confirm whether or not the data actually exists. It can also explain why the data is not being released, and the response time and type of exemption claimed can be quite revealing in themselves. It is also wise to consider the international mechanisms for requesting data. This is important if collaborating organizations outside of the United States are involved, such as the European Space Agency, JAXA, and other space agencies. Each of these organizations has its own data policies and request procedures, so coordination between multiple agencies may be necessary. This would be the case if the Atlas observations involved international partners. Fifth, it is helpful to cross-reference the information with the mission logs, as spacecraft operations generate very extensive logs. Attitude control data, for example, shows precisely where the spacecraft was pointing at any given time. Power logs will show when the various instruments were active and drawing power. And communication logs can tell us when data was being transmitted back down to Earth. These technical records, when taken together, provide a detailed reconstruction of the spacecraft's status. They show its activity at any given moment, and some of this telemetry is archived and can be requested. Mission operations centers maintain these comprehensive logs for the purpose of troubleshooting. They are also used for mission reconstruction, and although the most detailed telemetry may not be found in the public archives, it does exist, and it can be requested through the appropriate channels. So if the logs happen to show that a camera was on and pointed at the Atlas coordinates, but no images appear in the archive, then that is a discrepancy that is certainly worth investigating further. Such gaps could indicate that a loss of data during transfer, an error in the archiving process, or perhaps processing decisions that excluded certain observations from the archive. Each of these possible explanations has different implications and would suggest different follow-up actions. Sixth, you can check the checksums and version histories, as digital files have these checksums. These are hash values that verify the integrity of the data, and archives should maintain them. This should be done along with version histories that show when the files were added to the system. Modifying or replacing this metadata is a very important step. This is to ensure the data has not been corrupted or manipulated, a standard for reputable archives. They maintain detailed information about the data's origin. It is helpful to request the checksum logs for the relevant time periods and to gently look for any unusual gaps. Also, look for files that show a modification date after they were initially archived. This can quietly reveal if the data was altered. deleted, or if an issue arose that required reprocessing. Legitimate reprocessing happens quite often as calibration methods improve, or when errors are found, but this history must always be documented and made transparent. It can be useful to compare checksums with multiple backups if the data is distributed across different archive sites. Any differences between these backups may indicate a small issue with data integrity or synchronization. You can also cross-reference the file timestamps with the mission's own event logs. This helps to verify whether the file modification dates align with any reprocessing activities that have been documented. Seventh, you can reprocess the publicly available frames. Even if specific frames of Atlas are not identified, you can download and analyze all the Psyche images from the relevant time periods. Modern image processing can sometimes extract information that automated processes might have missed by stacking them. You can search for faint sources and check to see if Atlas might be visible in the background fields, even if it was not the primary target. You could also apply modern detection algorithms, like source finders based on machine learning. These can sometimes reveal a faint object that automated processes may have overlooked. Convolutional neural networks, which have been trained on images of asteroids, and comets, can be very good at identifying faint moving sources against a field of stars. Difference imaging, which involves subtracting a template star field, can help highlight transient or moving objects. It is wise to check the metadata carefully, as sometimes objects appear in the images, but are not cataloged because they were not quite bright enough to trigger the automatic detection threshold, or perhaps because their movement caused them to appear as an artifact. A gentle human inspection of these candidate detections can often identify real objects that the automated systems may have dismissed as simple noise or a cosmic ray hit. Eighth, you could form a citizen audit coalition. This is often too much work for one person, so organizing a collaborative effort that brings together amateur astronomers can be very helpful. Data scientists and planetary scientists, all ready to lend their expertise. Lawyers who understand the Freedom of Information Act processes, and of course, programmers. They could build tools to gently explore the archives, distribute tasks, and share any findings. We would maintain transparency about our methods and results, using collaborative platforms like GitHub to share code. We could use Slack or Discord for coordination, and cloud storage to help distribute the data. We would establish clear documentation standards, so that everyone's work could be thoughtfully verified. And then this work could be built upon by others, much like the wonderful amateur astronomy community. They have shown a remarkable ability in similar projects, such as discovering transiting exoplanets. Classifying galaxies and quietly monitoring variable stars have also been areas of contribution. All of these fields have benefited from citizen science efforts, a gentle combination of distributed work and diverse expertise. This collective approach often helps us notice things that individual researchers might happen to overlook. Ninth, we can consider channels for whistleblowers, if the data does exist. But it is perhaps being held back for reasons we don't understand, and insiders may know more. We could establish secure communication channels for potential whistleblowers to share what they know, anonymously. This would need to be done with great care, and with thorough verification. This is to prevent any hoaxes, but we know that some information that comes to light, when it is genuine, has revealed important details in past scientific discussions. We could use encrypted communication tools and establish verification protocols to gently assess reliability, and we would carefully protect the source's anonymity, ensuring the whistleblower is safe. This requires both technical security and operational discipline to prevent accidental identification through metadata or through behavioral patterns. It is wise to be prepared for misleading clues. Anonymous channels can attract both genuine information and, at times, deliberate misinformation. Verification is therefore essential, and any claim must be carefully cross-checked. It should be compared with verifiable facts, as extraordinary claims do require extraordinary evidence. This is all before anything is seriously considered or shared publicly. For our 10th point, E. We can parallel this gentle search with some public encouragement, such as writing letters to the observatory director, or to the mission's principal investigator, or the head of the funding agency. We could petition for open data policies, and for faster release schedules, and for better accessibility to the archives. Scientific organizations often respond to genuine interest, especially from their stakeholders, and when it is demonstrated in a clear and thoughtful way. A community's interest in these questions can gently influence how priorities are decided through the use of social media and thoughtful science journalism, and public forums to softly raise awareness, sometimes in institutions. Response is prompted by public interest, especially when internal advocacy has not yet found its way. This widespread fascination can serve as a gentle nudge for these agencies, encouraging them to allocate resources for data archaeology, for information that might otherwise remain hidden away in archives. Instead of simply waiting for eventual processing, it helps to engage with science communicators, who can translate these complex technical matters into compelling and gentle narratives. Consider the story of a quiet search for the hidden observations of a mysterious object. It holds a natural appeal far beyond the expert community, and this wider attention can bring forth resources and support in a way that internal advocacy alone sometimes cannot. This is not a swift process. It calls for a great deal of patience and considerable technical skill, and a quiet resilience when faced with bureaucratic hurdles. And yet, it is entirely possible. Every step is well defined, using tools and procedures that are already in place, and there is precedent in other data archaeology efforts. The question is whether enough people feel moved to invest their time, and their effort the potential reward, after all, could be immeasurable. If these elusive images of Atlas do exist and can be gently brought to light, they could offer a definitive answer to the question, providing high-resolution views of the object's form, its structure, and whether or not it possesses a tail. We could see if it has geometric features, or if its appearance is entirely natural. Such data, if it exists, holds the key to moving from gentle speculation to quiet certainty. And even if the data does not exist, if this careful search yields no results, that in itself is valuable information. It tells us that a window of observation was missed, that priorities were placed elsewhere, differently than we might have wished. An opportunity was simply not taken. This understanding helps to inform how we might plan for future observations, how we advocate for different mission priorities, and how we reflect upon what is observed and what is left unseen. And so, the quiet search begins now. The tools are available to us. The methods are clear. All that is needed is the will to gently pursue it, and a community to support the endeavor, because the answers we seek do not simply arrive by waiting. They come from a patient and careful search part. 12 experimental tests and what new observations might be made would help to eliminate or confirm alternative models. Even if we never capture a perfectly clear image, we are not without options. There are still observations we can gently make. These are experiments that would help us distinguish between the competing ideas about Atlas. To find out what it truly is, allow me to outline the key tests we could perform. I will explain what they would measure and which results might lead us to let go of or to embrace each model. The first test is high-resolution polarimetry at many different phase angles. Polarization measures how the electric field of light gently oscillates, and different materials polarize light in their own unique ways. This fundamental property of electromagnetic radiation provides us with a wonderfully powerful diagnostic tool. It helps us to understand a surface's composition and structure, all without ever needing to touch the object in question. You see, dust particles scatter sunlight, creating their own distinct polarization patterns. These patterns are quite predictable, depending on the particle's size, its composition, and its shape. The physics behind this is well understood. When unpolarized sunlight drifts into a particle, the scattered light becomes partially polarized, with its degree and orientation revealing information about the scattering particle. Metallic or crystalline surfaces create polarization signatures that are very different from soft, fluffy aggregates. Smooth, reflective facets differ from rough textures, and ice crystals have their own characteristic patterns as well. By observing Atlas at different angles between the Sun, the object, and our Earth, which is what astronomers call the phase angle, we can measure how the polarization changes across that geometry. From this, we can begin to infer the surface properties with a considerable amount of precision. The phase angle is important because the way light scatters depends on the viewing geometry, such as forward scattering, back scattering, and side scattering. Each of these produces its own characteristic polarization curves. If the polarization signature happens to match that of typical cometary dust, that would support the natural hypothesis. Cometary dust has been studied for many decades, so we know very well what we should expect. We would look for certain trends with the phase angle and specific degrees of linear polarization. We'd also look for specific wavelength dependencies. If it shows patterns consistent with metals, or ice crystals, or geometric structures, that would be rather unusual. Artificial surfaces, for instance, might show an uncommonly high level of polarization, or geometric patterns that are inconsistent with a random distribution of particles. The necessary instruments for this already exist. We have polarimeters on large ground-based telescopes, and perhaps even the Hubble Space Telescope. If observing time can be secured, the technology is quite mature. What is needed now is dedicated observing time and careful calibration to achieve the precision we seek, which is essential for discerning the subtle differences in its cometary behavior. A second experiment would involve narrowband imaging during its quieter, more dormant phases. You see, most gas imaging of Atlas has been conducted near its perihelion, when the sun's warmth naturally encourages its activity. This is quite understandable, as objects are at their brightest when they are nearest to the sun, and that is when most of our observational resources are typically directed. However, this focus on its closest approach means we could potentially be overlooking very important evidence about what truly fuels the activity of Atlas, observing it when it is much farther from the sun, using special narrowband filters that can isolate the light from specific elements, such as carbon monoxide, carbon dioxide, and water, would be very insightful. These filters are often only a few nanometers wide, gently blocking the general light and revealing the faint emissions from these specific elemental changes. If the object were an ordinary comet, this emission would fade quite significantly as it moves far from the sun and becomes cold. The relationship between a comet's distance from the sun and its activity is a well-understood pattern. Beyond approximately 3 astronomical units, most of the emission from water simply ceases. Carbon monoxide lingers a bit farther out, but even its signature eventually fades away. If this emission were to continue when we expect it to stop, if the gas production remained noticeable, without the sun's warmth to drive it, that would certainly call for an explanation. Natural processes, like the release of stored heat or the slow process of radioactive decay, could explain some lingering activity, but there are always limits to how much they can account for. The interior of a comet can indeed hold on to warmth, and certain isotopes can generate a gentle heat, but it is not enough to sustain major gas production at such great distances. Significant activity beyond 5 astronomical units, for example, would be quite extraordinary, and it would suggest either a very unusual composition or an internal source of energy beyond what the sun's warmth provides. An observation campaign should ideally span multiple orbits, gently tracking Atlas from its closest approach to its farthest point and back again, documenting when the activity begins, when it reaches its peak, and when it finally subsides. By comparing this curve of activity to its distance from the sun, any departure from the expected models would provide gentle clues about its internal structure and its source of power. A third experiment would be to create deep images using adaptive optics or a space telescope. This involves taking the highest resolution images possible and carefully layering tens or even hundreds of exposures in order to maximize our sensitivity to very faint and delicate structures. Image stacking is a well-established technique where we gently combine many different exposures. In this process, random noise tends to average out and fade away, while the true signal quietly accumulates. Features that were once invisible in a single frame can slowly emerge into view within these deeper, combined images. We could also use adaptive optics on the very large telescopes we have on the ground. Telescopes such as Keck or the VLT use this to gently correct for the blurring caused by our atmosphere. These remarkable systems carefully measure the atmospheric turbulence in real time. They then subtly adjust flexible mirrors to compensate, helping to achieve a nearly perfect, diffraction-limited resolutions. Another path would be to request time with the JWST or HST to capture images, not only spectra. You see, space telescopes are able to avoid the atmosphere's distorting effects entirely. They can also perceive wavelengths blocked by Earth's atmosphere, which would be helpful if Atlas has any kind of extended structure. Any hint of asymmetry or geometric features would be gently revealed by deep, high-resolution imaging. A perfectly symmetrical point source would be quite unusual, as natural objects almost always have their own unique irregularities. Even if they are subtle, a comet's nucleus is uneven, and the surfaces of asteroids are marked with craters. And even objects we might describe as symmetrical often show gentle variations in brightness across their surfaces. We would be looking for jets, fans, or shells, the typical structures that active comets often display. We would also be searching for any geometric patterns, such as straight edges or very regular shapes. By taking images at multiple wavelengths, we can carefully separate the light from the dust continuum from the light emitted by gas. This allows us to create color maps that show compositional variations. And we can also use a technique called differential imaging. This involves gently subtracting images taken at different times to softly highlight any changes that may have occurred. The resolution requirements do present a gentle challenge, as we would need to resolve features on the scale, and of the nucleus itself, perhaps down to tens or even hundreds of meters, if that is possible. Achieving this would call for either a space telescope or one of the largest ground-based instruments. This would be paired with excellent adaptive optic systems, all operating under nearly ideal conditions. A fourth approach would be to conduct coordinated, multi-wavelength monitoring. We could organize a campaign that brings together radio telescopes and X-ray satellites, along with optical instruments, all observing Atlas in harmony. This would happen at the same time, during one of its active cycles, which requires a great deal of coordination between facilities. It would also need careful, advanced planning and a willingness from the time allocation committees to support it. This would essentially be an exploratory journey of quiet discovery. The goal would be to find correlations. For instance, if a brightening in optical light coincides with bursts of radio waves, this suggests an electromagnetic activity that extends beyond simple thermal radiation. If these features were to align with the gas ejections observed through spectroscopy, it would imply that specific plasma processes are at play, creating high-energy photons. If everything fluctuates independently, this would be consistent with a natural, chaotic activity, a state where different processes simply operate on their own distinct timelines, for reasons that are not connected. However, a synchronized behavior across these unrelated wavelengths would be truly remarkable. It would point to organized mechanisms of energy release, unlike the natural, chaotic processes, which typically do not show such a close correlation across different wavelengths, unless there is a common triggering mechanism or a highly organized process of energy transfer. The rhythm of these observations is also quite important, as some phenomena unfold over timescales of just minutes or hours, which calls for continuous monitoring. Other events might take place over several days or even weeks during an observation campaign. We need a long enough time frame to catch these fleeting events, while also maintaining a long-term, continuous watch to establish a baseline of normal behavior. For our fifth experiment, we will monitor for coincidences with neutrinos and cosmic rays. Now, this is a bit more challenging, as it requires a touch of good fortune, as well as access to the data streams from neutrino detectors. Neutrinos are famously elusive, requiring immense detectors buried deep underground, or deep beneath the ice. You see, most cosmic neutrinos pass right through the Earth without ever interacting. This means the detection rate is very low, and most of the detections we do find are actually events originating in Earth's own atmosphere, or from other, more distant astrophysical sources. Still, we can propose that facilities like IceCube and Antares flag any neutrino detections. That happened to coincide with our Atlas observation window. These wonderful detectors record every single event with precise timing. Once we are granted access, searching their databases for these coincidences is a computationally straightforward task. We can also check the cosmic ray detector networks, looking for any excess of events while Atlas is active. Large arrays, such as the Pierre Auger Observatory and the Telescope Array, are constantly monitoring the cosmos for high-energy particles. The probability of a random coincidence can be carefully calculated. Using the known detection rates and our observation window, we can begin to determine just how many coincidences we might expect to see from pure chance alone. Finding a statistically significant correlation would be astonishing, and it would immediately elevate the importance of Atlas into a high-energy astrophysical event, as comets are not known to emit neutrinos or detectable cosmic rays. If Atlas were to do this, the physics governing its behavior would fall outside of standard cometary processes. Our detection capabilities are limited, so unless Atlas were to generate a considerable flux of neutrinos or cosmic rays, we would not detect anything. But the potential reward, conclusive evidence of high-energy particle acceleration, justifies the effort, especially since a search of existing databases would require minimal resources. Test number 6, rotation and light curve analysis. As comets and asteroids rotate, their brightness naturally fluctuates, as different parts of their surfaces turn to face the sun and the observer. This fundamental reality of solar system dynamics provides another diagnostic tool. A detailed analysis of the light curve can reveal the rotation period, the orientation of its axis, and sometimes even a rough model of its shape. If Atlas shows regular, periodic fluctuations, the period and amplitude can inform us about its shape and rotation. A short period suggests a small, cohesive object. A long period might indicate a large object or even a state of tidal lock, with some external influence. Fluctuations in amplitude also tell a story. Large variations suggest an elongated or irregular shape, while small fluctuations suggest a more spherical object or a particular viewing geometry, where we are looking down its rotational axis. If the light curve is unusually stable, too smooth, lacking the irregularities that naturally tumbling objects exhibit, that would be an anomaly. Real asteroid and cometary nuclei have surface features, patches of light and dark, and varied terrain that create irregularities in the light curve. A completely smooth light curve would suggest one of two things: a remarkably uniform surface, or an active compensation force, the natural fluctuations. If the variations were to correlate with other activity indicators in ways that suggest control rather than simple inertia, that would be quite noteworthy. For example, if pulses of gas emission always occurred at specific rotational phases, that would indicate deliberately placed, localized vents. If a change in brightness leads or slower rotational phases in ways that don't quite align with simple solar warming, This would gently suggest that active processes are regulating the output. The observation program would then require sustained monitoring throughout, complete rotation cycles, which could last anywhere from hours to days. Automated telescopes and monitoring networks can provide this kind of continuous coverage. By using multiple locations at different longitudes, we can ensure 24-hour coverage. The data analysis for this is a well-established process, using standard techniques to look for periods and to gently invert the light curves. For our 7th test, we can detect a magnetic field through a process called Faraday rotation, where radio waves passing through magnetized plasma experience a shift. The polarization angle twists in proportion to the field's strength and the plasma's density, an effect predicted by classical electromagnetism and observed in many astrophysical settings, which provides a direct probe of magnetic fields. If Atlas has a magnetic field in an ionized coma, radio sources should be visible through the coma. This would show a telltale rotation, which requires a specific alignment where Atlas passes in front of or near a bright radio source. As seen from Earth, these kinds of events are quite rare, but they can be predicted by using orbital calculations and source catalogs. This is technically a delicate task, requiring very precise polarization measurements of the radio sources along the line of sight at multiple points in time. The measurements must be accurate to a degree, or even a fraction of a degree, in their angle. The Faraday rotation caused by our own ionosphere must also be carefully calibrated. This is because Earth's ionosphere also rotates the polarization, but this can be accounted for with VLBI networks. This could allow for the direct detection of fields that shouldn't ordinarily exist around a natural comet. Comets typically do not have their own intrinsic magnetic fields. Their nuclei are too small and non-metallic. Any detection of a field would be quite extraordinary, as it could indicate a metallic component, an internal dynamo, or active electromagnetic systems beyond known natural processes. The field's strength and structure would help us constrain the models of what might be generating it. Each of these tests offers its own set of predictions under different models. For example, if Atlas is a natural comet with an unusual composition, we would expect to see comet-like polarization activity only when it is being warmed by the sun. We might also see an irregular shape and rotation with no multi-wavelength correlation, and no indication of a magnetic field if it is just a cloud of debris. We might anticipate a somewhat unusual polarization from the collective scattering of light from an extended, yet compact, structure. Its light curve would likely be gentle and chaotic, showing no signs of organized electromagnetic activity. If it were to show electromagnetic activity through natural, albeit peculiar, processes, we would then expect to see an unusual polarization. We might also detect a magnetic field that correlates across multiple wavelengths of light. Activity could be possible even when it is very far from the sun, if it were of artificial origin. While nothing is certain, we might perhaps observe geometric structures. We might notice organized behavior, or emissions that do not seem to match any known natural spectrum. There could be temporal patterns that suggest a sense of control. The key is that these ideas can be tested. We can gently outline beforehand what kind of results might support or perhaps contradict each idea. For each hypothesis, we can make predictions. This is the quiet way that science works. You then test those predictions and slowly update your understanding based on what you find. What would not be helpful is to continue gathering observations that remain ambiguous, the kind that could be interpreted in many different ways, depending on one's existing perspectives. Instead, we need observations that are designed to gently resolve this ambiguity, to guide us toward a conclusion and softly rule out possibilities. A coordinated effort is needed. This means carefully allocating time on our telescopes. It means prioritizing these questions, and a willingness from observatories to dedicate their resources to what may seem like a distant inquiry, but one where the potential for scientific discovery is immense. Either we may find that Atlas is a peculiar comet, and in doing so, learn something new about the physics of comets. Or we might discover it is something else entirely, opening up a whole new path for us to explore. New observational facilities are on their way, and Atlas will have future close approaches to the Sun. This means there will be future periods of activity, and with them, future opportunities to learn. The question that remains is whether the astronomical community will embrace these moments, or if Atlas will simply remain a curious footnote in the catalog of interstellar objects. If it were to be artificial, the implications for our policies and scientific procedures would be profound. Let us gently consider these implications. If we are to accept the possibility, even hypothetically, that this object, Atlas, might not be of natural origin, if so, everything would gently shift. The very frameworks we use, the ones we use in our search for extraterrestrial intelligence, the policies that guide how we approach such discoveries, and the procedures for confirming extraordinary claims, all of these would need to be thoughtfully revisited. We can begin with the traditional SETI protocols, which involve a search for radio signals. These are beacons, purposefully transmitted by technological civilizations. The underlying assumption is that this communication is a deliberate attempt to make contact. It is presumed they use electromagnetic radiation at particular frequencies, originating from systems of planets that are orbiting other stars. However, what if technological artifacts could travel between the stars if they were small enough and numerous enough, as some see, that we might encounter them within our own solar system? The search space would be completely transformed. An artifact would not necessarily need to transmit a signal. It might lie dormant. It could be passively observing, or perhaps operating on principles that we do not recognize as communication. Detection, in this case, would come from unusual behavior. It would come from physical properties that are inconsistent with known natural processes. It would not come from a decoded message. This gently shifts the focus of SETI away from radio astronomy and toward optical surveys, spectrometry, and astrometry. Essentially, it would involve any method that might identify unusual objects. Among the millions of natural celestial bodies that we currently monitor, the threshold for detection also shifts. Traditional SETI has always set a very high bar for declaring a signal to be artificial, because the consequences of a false positive, says, are quite serious, both professionally and socially. But if artifacts were to be physically present and available for observation, the burden of proof would shift. We would have the potential to examine them directly, gathering multiple lines of evidence, and performing tests that a simple radio signal would not permit. The standard then becomes D. Whether the behavior of this object, across all methods of observation, is more consistent with artificial models than with natural ones. Policy questions would then become quite pressing. Who would own the data if an artifact were to be confirmed at present? Space agencies maintain control over their own mission data. However, the discovery of non-human technology could activate different areas of jurisdiction. National security agencies might possibly claim authority. International bodies, such as the United Nations Committee on the Peaceful Uses of Outer Space, D, might also assert responsibility. The legal frameworks for handling such a discovery do not truly exist in an actionable form, and the protocols for scientific disclosure are even less defined. The International Academy of Astronautics does have principles that outline how to handle the detection of artificial signals. It is gently stressed that international notification and scientific verification should come before any public announcement. But it is worth remembering, these are voluntary guidelines, not regulations that can be enforced. And they were written with the gentle assumption of a radio signal detection, not a physical artifact. If a spacecraft were to happen upon an image of something seemingly artificial, who then decides when and how that information might be released. The chain of care for the data becomes so very important. Any claim of detecting technology from beyond will be met with a great deal of thoughtful questioning, as it should be. The only way to gently move beyond that questioning is with data whose integrity is beyond any doubt. This could include things like raw frames with securely signed headers and multiple independent observations. It would mean carefully cross-checking the same phenomenon and maintaining open archives for the data. These would be open spaces where anyone could attempt to recreate the analysis with a clear and well-documented methodology. Documenting every step of the process would be needed, as anything less might invite suggestions of error, or even misinterpretation. International cooperation would be essential, but also quite a delicate matter. Different nations, of course, have different interests in the quiet expanse of space. They have varying levels of openness and different relationships between their space agencies and their military organizations. An artifact discovered by one nation's spacecraft might be considered a strategic asset, rather than scientific data to be shared openly. Finding a gentle balance between the scientific principle of openness and concerns for national security would require conversations at the very highest levels. Historical comparisons can only guide us so far. The discovery of pulsars in 1967, for example, led to some quiet speculation about artificial signals, before the lighthouse model gently explained them as rotating neutron stars. The WOW signal in 1977 remains unexplained and has not been heard from since. Neither of these two cases called for the kind of policy response that a physical artifact would seem to require. Perhaps the closest parallel we can draw is how the discovery of the DNA structure, or nuclear fission, required international scientific cooperation and the careful development of policy, although even these examples don't quite capture the full scope of such a moment. The ethical questions gently multiply. Should such an artifact exist? Does it belong to the one who finds it? Does it belong to all of humanity, together? Or does it belong to whomever sent it? Do we have the right to study it, to interact with it, to attempt to communicate? What if it is observing us? What might happen if we were to disturb it in its journey, setting in motion responses that we cannot fully anticipate? Though speculative fiction has certainly explored such possibilities. However, these scenarios would move beyond the realm of fiction should we ever truly encounter such a situation. There is also the delicate matter of a premature announcement, a declaration of non-human technology made too soon, which, if based on insufficient evidence, could harm credibility and perhaps hinder the progress of earnest SETI endeavors, inviting skepticism and making any future claims more challenging to assess with fairness. Yet, holding on to evidence, while demanding ever higher thresholds of certainty, could also be a disservice. If the phenomenon is indeed real and of great importance, finding the appropriate balance requires a kind of judgment that is difficult to codify into procedures, and we must also consider the public's reaction. How might the disclosure of non-human technology gently ripple through our society? Some would surely be filled with wonder, seeing it as humanity's most profound discovery. Others might feel a sense of unease, a deep-seated apprehension of intrusion or an existential threat. Still others would remain unconvinced, regardless of the evidence, perceiving elaborate deceptions or contrivances. Gently navigating the societal impact while upholding scientific integrity will likely be the most delicate challenge of all. What seems clear is that our current frameworks are not quite adequate if Atlas, or any other object, turns out to be of artificial origin. We find ourselves unprepared institutionally, procedurally, and culturally. This does not suggest we should cease our search or refrain from investigation. It does not mean we shouldn't follow the data wherever it may gently lead. It simply means we ought to begin developing these protocols now, well before we might need them, so that if the extraordinary does become reality, we have structures in place to handle it with care and responsibility. The scientific process itself would be iterative: observation, the gentle forming of a hypothesis, prediction, testing, and thoughtful revision. It is the same method that has served so well for every other scientific question. The difference lies in the stakes and the scrutiny. Each step would be carefully examined by critics looking for any flaw. Every claim would need to withstand the most rigorous and thoughtful skepticism, which is as it should be. Extraordinary claims softly call for extraordinary evidence, and the process of gathering and confirming that evidence would need to be beyond reproach. Yet we must not allow the sheer difficulty of the task to render us immobile. The questions are there to be asked, and the observations are there to be made. The data, should it exist, can be uncovered and thoughtfully examined. What is needed, then, is the courage to gently follow these unusual paths with a quiet seriousness. It requires the care to avoid mistaken conclusions, and the openness to preserve the trust upon which our framework is built. We simply need to apply it with gentle consistency, even when its implications lead us to places that feel unfamiliar. The truth is, this process has already begun, whether we choose to acknowledge it or not. Every quiet observation of Atlas, every thoughtful analysis of its unique properties, and every gentle attempt to understand its behavior is already a part of this quiet investigation. We are simply not yet approaching it with the focused, systematic attention it may gently call for. And so, the question before us is a gentle one. Will we continue on with these scattered, separate observations, each one uncoordinated, leaving a sense of gentle ambiguity to linger in the air? Or will we instead begin a focused and thoughtful journey, one that is carefully designed to find clear and gentle answers? Should Atlas prove to be of an artificial nature, eventually we will come to know. Technology leaves behind whispers that cannot remain hidden forever. Its structure, its composition, its patterns of movement, all of these will eventually reveal themselves with patient observation. The only question that remains is how long this unveiling will take, and how many quiet opportunities we might miss along the way, through our own hesitation or lack of gentle coordination. And even if it is not artificial, coming to understand that with certainty holds its own quiet value. For it would mean that we have learned something new and wonderful about the vast scope of natural phenomena that our universe is capable of creating. In either outcome, it is the journey of inquiry itself that allows science to gently move forward. It invites us to refine our methods of detection, to improve the way we handle our data, and to develop ever more thoughtful models. It also asks us to contemplate how we might recognize intelligence, should we encounter it in an unexpected place. These are questions worth pondering, no matter what Atlas reveals itself to be. Part 14. A wider cosmic pattern. We find ourselves in a new era, an era of profound and quiet wonders. Let us take a gentle step back and look at the larger picture. We have Atlas, moving in a way that is unlike any comet that we have ever seen before. We have ASCAP J1, 832, which pulses gently in radio and X-rays with a 44-minute rhythm that does not seem to belong to any known family of objects. We have observed a single neutrino, carrying an energy of 220 petaelectron volts, a quiet indicator of particle acceleration that we cannot yet fully understand. Are these simply isolated curiosities, or are we perhaps gently stepping into a new age? The universe, it seems, continues to reveal itself in ways far stranger than we could ever have imagined. Let us consider what has shifted over the past 10 years. With survey telescopes like the Speedy Rapid Response Facility, Pan-STARRS, and the Vera-C, Rubin Observatory now sweep across vast stretches of the night sky, again and again, gently searching for anything that flickers or drifts. While radio arrays like ASCAP and Meerkat keep a constant, quiet watch over the heavens, finding fleeting events that might otherwise go unnoticed. Events that earlier instruments would have missed entirely. even our neutrino detectors, have gracefully evolved from small, experimental setups into vast, cubic kilometer instruments. Our gravitational wave observatories have softly opened an entirely new window onto the cosmos. With each new capability, we uncover phenomena we never knew were there. Fast radio bursts, for instance, were not discovered until 2007, and this wasn't because they are rare, but simply because we weren't looking in the right way. Now, we can observe tens of them each day, and yet, we still don't fully understand what brings them into being. The merging of neutron stars was once only a theory, until we observed one in 2017, through both gravitational waves and electromagnetic radiation at the same time. The universe continues to fill us with wonder, precisely because we are, at long last, truly beginning to look at it. With full sensitivity and complete coverage, machine learning and artificial intelligence are gently guiding this process forward. Algorithms can now softly sift through millions of images, spectra, and light curves, searching for patterns and anomalies that would take a human observer many years to identify by hand. This simply means that we are now discovering these outliers far more quickly than we are able to explain them. The catalog of unexplained phenomena is growing more rapidly than the catalog of those we have come to understand. But there is a quiet paradox in all of this. More data often means more noise. More surveys can mean more statistical flukes and more instrumental artifacts that are mistaken for genuine signals. It means more false positives. When you are gazing at billions of objects, a 1 in a million event happens thousands of times. How? Then, do you distinguish genuine new physics from the statistical outliers that are certain to appear in such large collections of data? The answer, it seems, lies in correlation and replication. If the strangeness clusters around certain types of objects, within certain regions of space, or during specific intervals of time, that suggests something real is at play. If the anomalies are scattered randomly, appearing just once and never again, they are likely just noise. Odd Atlas is strange. Yes, but it is a real object. 832 is a peculiar object, and the neutrino, a singular event. One wonders, are they connected? Are there other such pairings that we are gently passing by, unnoticed? Or, perhaps, are we simply matching patterns across insufficient data, seeing connections that do not truly exist? Recent discoveries beyond these specific examples hint at the broader scope of what we do not yet understand. For instance, astronomers have found exoplanets with atmospheres, that should not, in theory, be stable, given their orbital configurations, which are models of formation. Find very difficult to explain, along with densities that seem to require quite exotic compositions. There are also stars that dim in irregular ways, like Tabby's star, which prompted quiet speculation about vast orbiting structures. And before clouds of dust were shown to be the cause, there were observations of galaxies that seemed to contain no dark matter. In contrast, we find others with a great abundance of it, which challenges, our fundamental understanding of galaxy formation. As we move toward the year 2025, we are also beginning to see a gentle acceleration in discoveries aided by artificial intelligence in the field of astrophysics. Neural networks are now searching for gravitational lenses and identifying anomalous spectra from distant starlight. They are predicting stellar evolution with a precision that surpasses our more traditional models. And yet, AI can only find what it is trained to see. If the training data does not include certain artifacts or truly novel phenomena, it is possible the algorithms may simply overlook them, or they might classify these new things as mere noise. It makes one wonder if we are becoming reliant on tools that could systematically blind us to that which is truly and beautifully unexpected. The philosophical question that rests beneath all of this is whether we are uncovering genuine strangeness, or if we are manufacturing it through our own observer bias. Has the universe always been this peculiar? Are we only now seeing it with enough clarity to recognize that quality? Or perhaps, is strangeness itself a relative thing? Is it simply defined by how much an observation deviates from the models we currently hold dear? And as our models improve, will they simply absorb what now appears to be so anomalous? I find myself leaning toward the former thought, that the universe has no obligation to conform to our human intuition. It does not need to follow the physics of the 19th century. Quantum mechanics, after all, is wonderfully strange. General relativity is strange. Dark matter and dark energy are profoundly and deeply strange. It seems each generation of physicists finds that reality operates on principles that feel, at first, quite bizarre. That is, until you begin to understand them. And even then, they never cease to be utterly fascinating. So perhaps we are simply living through a wonderfully strange era. Perhaps the 21st century is the time when we finally have the gentle tools to see the universe for what it truly is. For it seems to be a place replete with the most extreme conditions, a place of strange processes, immense scales, and energies that gently push the laws of physics to their very boundaries. Atlas and ASCAP, J1, 832, along with the ultra-high energy neutrino, may simply be the first hints of a much larger catalog. So, of cosmic wonders, quietly waiting to be discovered. Or perhaps, we are simply reading too much into these outliers, seeing faint patterns within the randomness. Perhaps we are letting our imaginations drift just ahead of what our data tells us. The only way to truly know is to continue our patient observations and our careful experiments. We must continue to place our most imaginative hypotheses under the gentle discipline of measurement. Science moves forward by considering what might be mistaken, yet investigating these ideas with enough care to find the truth. What is certain is that we are living through a truly remarkable time. In astronomy, as discoveries are unfolding more rapidly than ever before, the questions are becoming deeper, and the answers all the more surprising. Whether Atlas, in particular, represents something truly out of the ordinary, or if the only true anomaly is simply the fact that we can now study an interstellar object in such wonderful detail, contemplate its meaning, and propose tests to gently probe its very nature. This represents a capability that just one generation ago would have seemed like pure science fiction. And more interstellar visitors are on their way. Borisov, after all, came before Atlas. Statistical models suggest that tens of these objects pass through our inner solar system each year. Most are too faint for us to see. But the Vera C, Rubin Observatory, once it is fully operational, we'll find them by the hundreds. Each one is a quiet messenger from another star system, carrying with it information about the conditions and processes in environments that we may never visit directly. Each one is an opportunity to test our own assumptions. And perhaps to discover that we were mistaken about the very things we thought we understood. The strangeness may have only just begun, and that is an exciting thought, even if it is also a little unsettling, because it means the universe still holds its secrets, still holds surprises for us. It still has the power to gently shift our comfortable certainties and invite us to think more deeply about what is possible. Part 15. A final synthesis. What we truly know. Let us consider what we should ask, and how 3 particular tests might help us find the answers. Let's gently ground ourselves for a moment and summarize what we truly know with certainty. We will separate speculation from established fact, and in doing so, we can clarify the path forward. This is what we currently understand. The test involved stacking more than 9,000 frames of the object known as Atlas, and it revealed no extended coma, leading to the conclusion that it is a point-like source of light. This represents solid, verifiable data. In addition, the JWST and other infrared instruments have gently detected the emission of carbon dioxide and water vapor, which suggests some form of volatile activity. And these observations also lend a quiet strength to the telescope's findings. On the ground, our optical telescopes have reported a variety of results. Some have noticed a subtle asymmetry. Others, however, have observed very little structure. These observations are all real, yet they do not seem to align consistently. Observations from the Psyche spacecraft might help resolve these gentle contradictions, but they have not yet been shared publicly. And so, we do not know with any certainty whether these observations even exist. Now, let us turn to what remains unclear. We wonder about the physical mechanism that could produce gas without a visible dust tail. We are also uncertain about the composition and structure of the object's core, and whether the noted discrepancies between instruments reflect genuinely unusual behavior, or if they are simply the result of observational selection and differences in data processing. It remains a quiet question whether electromagnetic or plasma processes might be playing any kind of unusual role. And we ponder if any of the multi-wavelength phenomena we have discussed, such as ASCAP J1 point, so 832 and the high-energy neutrinos, Johansen, have any connection at all with Atlas. This brings us to the realm of pure speculation. There is the idea that Atlas could be artificial or technological in nature, and the thought that the spacecraft data from Psyche is being withheld for reasons that are not scientific. There is also the notion of a pattern connecting various cosmic anomalies, and so also through some form of shared, unconventional physics. These are interesting ideas, certainly worthy of exploration. They are worthy of being tested, but for now, they are not supported by any conclusive evidence. They remain as hypotheses, not as established facts. So now, let's consider a gentle scale of reasoning. How do we move from a natural explanation to a more unusual one, from the natural to the artificial? What kind of evidence would gently nudge us from one level of understanding to the next? A natural explanation is always our starting point, our default assumption. It simply asks that we find a plausible combination of composition, structure, and environmental conditions that can softly explain what has been observed, all without needing to call upon new forms of physics. Natural, yet perhaps beautifully strange. This would require us to identify processes at work on Atlas that are not typically observed in ordinary comets. However, these processes would still need to align with our known physics, perhaps as unusual electromagnetic or chemical effects. To consider an artificial origin, we would need several independent lines of evidence, each suggesting behavior that is inconsistent with any known natural process, and a structure that hints at intentional design. The data's origin must also be free of any error or contamination. 3 important tests could help us explore this. The first test involves a gentle, forensic recovery of archival data. This means accessing data from the Psyche spacecraft, or any other spacecraft that may have made observations. This would be during the Atlas observation window, simply to confirm whether any images were captured. We would then gently examine them for their structure and form, and carefully validate their metadata and processing history. This would be the most direct approach, as a high-resolution image would quietly reveal the true appearance of the object, helping us understand if it is a conventional, yet unusual, cometary nucleus, a cluster of fragments, or perhaps something with a more geometric shape. The technical challenges for this are quite low. While institutional hurdles might be considerable, they could be overcome with patience and persistence, and in respectful, formal inquiries. The second test would involve coordinated observations across multiple wavelengths of light. We could organize a calm campaign during Atlas's next active cycle, using polarimetry in the optical and infrared spectrums. This would include spectrometry to monitor for gas production, and radio telescopes to listen for any emissions. We would also have X-ray observatories watching for faint flashes, alongside sensitive particle detectors, monitoring for any coinciding high-energy events. Such a comprehensive approach would allow us to notice subtle correlations that might be missed by single instrument observations. It would help us to see if Atlas exhibits any form of electromagnetic activity, whether its behavior is cyclical or more random, and if it produces any signatures beyond what we would normally expect from a comet. The third test involves correlating high-energy events. This would mean continuously monitoring neutron detectors and the wider cosmic ray networks, as well as gamma-ray observatories, to search for any potential correlations that are statistically significant with the activity of Atlas. This would explore the most remote possibility that, Atlas is somehow connected to high-energy astrophysical processes. It is a distant thought, of course, but the data does exist within real-time streams. It can be gently analyzed, and should a correlation emerge, it would softly reshape our understanding of what this object might be. If no such correlation is found, it would simply rule out a category of more unusual explanations. This brings us to the 90-day roadmap. For days 1 through 30, the Citizen Audit Alliance will gently begin by dividing the archival search into smaller, manageable tasks. They will then submit Freedom of Information Act requests for related data and mission logs, and begin the process of downloading the system information. And they will also reprocess any available images from all missions that might have captured a glimpse of this object. Between day 30 and day 60, the results from the archival search will be compiled, and telescope proposals will be thoughtfully prepared for an observation campaign. They will coordinate within the next Atlas operational cycle, reaching out to the collaboration led by Team Neutino. A request will be made for a correlation analysis, and the campaign will then gently commence. From day 60 to day 90, there will be a public advocacy for data transparency, and the proposals will be submitted. They will follow up on the information request responses and share the preliminary findings from the archival analysis. Channels of communication will be opened with professional astronomers who are ready to contribute their expertise and telescope time. For anyone watching this, there is a way for you to participate. If you have skills in data science, you might consider volunteering to help search through the archives and to help develop new tools for analysis. If you happen to have access to a telescope, even a small amateur instrument, you can contribute observations during our coordinated campaigns. If you have legal expertise, your assistance with the information request processes and data access would be deeply valued. If you have a platform or an audience of your own, you can help by gently raising awareness of this endeavor and encouraging organizations toward greater transparency. If you have access to funding resources, you might consider supporting these citizen science efforts through grants or community fundraising. Every small contribution helps to move the timeline forward, from mystery toward an answer. At the very heart of this story, we find ourselves standing at a quiet threshold. We have observed an object that behaves in a way so curious, it asks for an explanation. We have the technology that could potentially provide that explanation, and we also have a choice of whether to pursue this understanding with gentle seriousness, or to simply let it remain a mystery. The simpler path would be to call it an unusual comet and simply move on. The more thoughtful path, however, is to acknowledge what we do not yet understand, and to commit ourselves to learning why. Science so often moves forward in these very moments. when our observations do not quite fit our expectations, when a standard model begins to strain under the weight of anomalies, a decision must be made. Whether to mend it with temporary explanations, or to consider that something more fundamental may be at play. Much of the time, these adjustments work quite well, and the standard model endures, becoming more refined and strengthened in the process. But on rare occasions, the anomalies are gently telling you something far more profound, something that asks us to reconsider our most fundamental assumptions. We do not yet know what kind of moment this is. Atlas could perhaps be a comet with unusual properties, yet ones that are ultimately understandable. Or it might be the very first clear example of something we have yet to classify, something natural, however strange, or in a scenario that sounds as if it's from a gentle story, but one we cannot simply dismiss without evidence. It could possibly be an artifact, the very first one discovered from beyond our own solar system. The likelihood of that last option is small, but being small is not the same as being impossible, and the implications are far too profound to ignore, simply because they may feel unsettling. What we do know is this: the mystery is open, and the tools to explore it are available. The tests have been defined. We do not yet have proof of the impossible, but we do have the most compelling clues that we have ever encountered, of something that does not quite fit within our current understanding. The data exists somewhere, resting in archives or within the instruments now gazing at the heavens. Right now, the question is whether we possess the collective will to pursue it, the rigor to do so properly, and the quiet courage to accept whatever answer may emerge. This is how discovery unfolds, not through a sudden revelation, but through the gentle accumulation of anomalies that invite new questions, through investigations that follow those questions, wherever they may lead, and through communities working together to transform observations into understanding. The mystery of Atlas invites us into that process, offering us a part to play in discerning what is real and what might be a misinterpretation. So, let us test it. Let us request the data, make the observations, and perform the analysis. And listen to what the universe is truly telling us. Because the only thing more unfortunate than discovering we were mistaken about something fundamental would be to have the opportunity to find that out and choose not to look. The frontier is open. The mystery awaits. And somewhere in the data we have yet to see, or in the observations we have yet to make, the answer is quietly waiting to be found.